Can everyone see my screen? Or actually, let me reshare actually. So I'm sharing the right screen. Okay, yep. Can everyone see that? Great. Okay, so hi guys. If you guys don't know me, I'm Sean. I don't know. I generally do a lot of math and I'm really excited about it. So I'm really excited to talk to you guys today. Um, I don't know. Basically, what I'm going for this lecture is that it's going to be generally really informal. I looked through all the past lectures that you guys received, and they all seem to be pretty competition oriented. But my philosophy for this talk is that I'll try to introduce you guys to a new problem, which is the angel problem, which isn't necessarily directly correlated with competition mathematics, but there are a lot of really interesting ideas that I think can be easily applied to a lot of combinatorics problems. And also just like, it's just a really pretty problem, in my opinion. If you guys have any questions, feel free to ask it in the chat. I'll be having the chat open. And yeah, so I guess I'll just get started. So today I'll be talking about the angel problem. You'll see this is labeled the University of Virginia REU 2021. This is because this is the research program that I'm attending right now, and I gave a talk there, and I'll be giving the same talk to you guys, which sounds a little scary, but don't worry about it. It's a really basic, but also a really interesting problem. The angel problem specifically is here. Can you guys all see that? I don't know if something's blocking. Okay, there we go. So basically, the angel problem is a turn-based game between the angel and a devil on an infinite grid. So basically, the angel has power p and can basically move at most p squares away, including diagonals. That's why I say L infinity norm. When I say L infinity norm, what I really mean is like it's like you can go diagonally in a sense. Like you just do max x, y. That's what it really means. Because the typical Euclidean distance, L1, is equal to square root, or L2, is square root of x squared plus y squared. So L infinity is max x, y. And so you can see the angel of power p can move anywhere in this square. So the angel moves somewhere, and then the devil removes one square from the grid. And they take turns. So the angel moves somewhere, the devil takes away a square, so on and so forth. You keep going like this. So for instance, here's an example game. So the angel is starting, the devil hasn't moved any squares yet. Angel moves, devil removes a square. Angel moves again, the devil removes another square. Angel moves again, the devil removes yet another square, and voila. That's basically how the game goes. So it keeps going like this: move, remove, so on and so forth. And so it seems pretty obvious that one of two things can happen, right? So either the devil can trap the angel in a finite amount of time. So for instance, after 1 billion seconds, the devil can eventually trap the angel in like a huge red box, or the angel can evade indefinitely. So the angel can keep running away from the devil. Obviously, one of these two things has to happen because, you know, if the devil can't trap the angel in finite time, then that means that the angel has to evade indefinitely. And so the natural question is, can the angel win for any power p? So for instance, for p equals 1 or p equals 2 or p equals 3, what's the, like, is there a possible strategy for the angel, or does the devil always win? Some brief background about this problem. The problem is due to John Conway in his book, along with his co-writers, I think Richard Guy and Ellen Berlekamp, in their book, Winning Ways for Your Mathematical Plays. Excellent book, from 1982. This is one of their puzzles. I think they call it, I'm not sure they call it the angel problem in that book, but it's basically this problem. I think they refer to it as a chess king or something like this. In any case, like a lot of good things, this is from John Conway. And it's also just a really simple problem. So also, just if you start thinking about the problem, well, who do you think is going to win? Like the angel or the devil? Like obviously your instinct should probably be the angel, right? Because the angel can move around a lot compared to the devil. The devil removes one square at a time, and the angel can move anywhere, right? So the angel should probably be able to win. Maybe, right? Because the angel should be able to move around like a lot. Like if p equals 100, then the angel can jump like really, really far away from any of the red squares that the devil ever does. But I'll take the next few slides to try to explain to you why it's not so obvious, why maybe the devil has a chance. In a sense, I'll be playing like the devil's advocate, if you will. So, well, first thing out of the way, the devil wins for p equals 1. This is not so surprising because p equals 1 is really small. But it's an interesting exercise, and I encourage you guys to think about it. If you guys don't want to know the solution, I think it's a really interesting problem, and it's also really Olympiad-like. So if you guys want to like tune out for a little bit, maybe for the next 2 or 3 minutes, that's also fine by me. I think it's a really interesting problem. So if you do want to think about it, feel free to just like come back in like 2 minutes or so, because I'll be explaining the solution. Oh, I guess. Hold on just a second. I pretty sure I've allowed candy. Okay, anyway, you guys can see it again, right? Yes, okay, cool. So the devil wins for p equals 1. Here's a given proof. If you guys don't want to look at the proof, feel free to tune away. So the idea is as follows, okay? So if you direct your attention to the first diagram, if at any point, if the angel's right here and there's like, oh, hold on just a second. Apologies, new laptop. Okay, so we want that there. Yes, okay. So if at any point the angel is down here, just chilling, and there are 3 red squares in front of her, well, the angel cannot pass this line, right? This line is totally blocked off to her. The reason is because, if you go this way, then you just shade it this way, and you keep going this way, you can just keep shading, right? Like, there's no way. You can always just keep these 3 squares in front of her. If you go this way, you could shade it this way, and if you go this way again, you shade this way. You just cannot pass this line, If at any point it looks like this, and then the angel is right here, the angel can't pass this line. So, in fact, I claim that the devil can block a line that is at least 5 squares away. So if the angel has like a 5 square lead, for instance, right here, then if the devil just says, okay, angel, I'm making sure that you do not pass this line, then the devil can guarantee it. And the proof of this is not so interesting, and it's also kind of obvious, because it's like, you can probably make something like this. All you need is something like this. Like the angel could be down here, and if you even have this, you can still, build a wall up here, and the angel can never pass. So the idea is a casework. So, in something like over here, and if the angel then goes over here, then I would shade over to here, then I would win, right? So let's assume that does not happen. So let's say the angel goes over here. Well, and if the angel goes over here, then you shade this, and the angel's dead, because if the angel goes over here, then so on and so forth. You could always make sure that there's 3 squares in front of her. So let's not move there or there. Let's move over here. We move over here. Well, not this square probably. I'm going to shade this square. Because the idea is that, I just want at some point to get 3 squares in front of her. So if I go over here, then, I can shade over here, and then now you're doomed, right? Because if you go here, then you shade here. If you go here, then I shade here first, and you can't really go over there or over there or over there. It's just like, it's a pretty basic casework bash. So if you go up here, then that means you can just shade this square. If you go up here, of course, you're probably going to shade this square, so on and so forth. It's a pretty direct check. And also the number 5 is not really that important. It's just that, eventually the devil can block off a specific line. Does that make sense to you guys? Yes, no? I enjoy a lot of feedback in the chat. So if you guys at any point want to perk up in the chat, that's also fine. Also, if you guys have any questions, feel free to ask them. I think one of the questions so far is, are you good at math? I like to think that I'm good at math. I don't know if I'm actually good, but anyway. Levying this lemma, this is the plan. So here's the plan for the devil to trap the angel. The angel is going to chill in the middle for a little bit and make a square that's big enough. I think 100 is definitely enough. I'm pretty sure even 30 is enough. But if we say this is 100, we're going to outline a plan. So we're going to first ask the devil to draw in all of these corners. Okay, each of these corners has length 5. Right? So this will take about 40 steps, and the angel in particular will not reach any of these green zones yet. So that's good. So the angel will be somewhere over here maybe. But the point is that the angel will not reach any of the green zones yet. So the angel's over here. We have all the corners. The reason we have the corners is that the devil wants to make these 4 distinct regions to fight the angel in. So if the angel at any point reaches here, let's say the angel moves a little bit and reaches here, then the devil just employs this strategy on her. So right here, then I would go here, then she'd go over there, then I go over there, so on and so forth. Just employ the strategy so that she could never pass this line. And we can do this because this is length 5. And if at any point the angel tries to it's oh crap, okay, I give up. Then you go over here, then you just trap her off over here. Eventually, she'll just be trapped off in this little cage, that's why I call it the cage. The idea is that at any point, if the angel goes in any of these green regions, then you just say, no, you're not going to pass. Does that make sense? So basically, the devil wins against a chess king. That's why this slide is called a chess king. Does that make sense? Because the chess king can move anywhere in this 3x3 region. Okay, well, it's sure. I mean, I guess you could, it's probably p equals 1 might not win, but that doesn't give me any reason that p equals 100 shouldn't win, right? And in fact, p equals 1 is really bad because, well, 1, you can't jump over anything, right? If the king, the reason that this dumb strategy works is because if the angel is right here, well, the angel can't jump over any walls, and that's not so good. But for p equals 100, she can not only jump over one wall, she can jump over like 99 walls, right? Like the angel clearly does not have very much maneuverability for a p equals 1. Yeah. So, the strategy for p equals like 5 or 6 or something, you'd imagine it's just like, okay, well, I could just keep moving up, like just like keep traveling up. And then every time like I run into some random red squares, I just try to get away from the squares. So it's like, it's like you're like in go-kart, like you're just like driving forward, and every time you come across an obstacle, you just dodge it. That seems pretty intuitive. Like for p equals 100 or something, this definitely should work, right? Not quite. If you tell this to Conway will think for a little bit and then be like, okay, he'll give you this definition. A fool is an angel who always strictly increases her y coordinates. So, an angel that keeps running up, maybe dodges left and right sometimes, but always keeps moving up. And, like just keeps moving up and dodges any of the like red squares. Can someone try to think of a possible strategy for the devil that could like trap the angel if the devil knows that the angel is always going to keep moving up? Any ideas? You guys don't actually have to respond, but it's nice to engage with the audience or whatever. Here's the idea. Well, if you're going to keep moving up like a go-kart, what if instead of just like putting a bunch of obstacles in the way, what if I just invest? Oh, someone says wait. Okay, if you want to wait, feel free to think of something. It feels intuitive, right? Like if an angel keeps moving up, then the angel should probably win, right? Like as in like, how can the devil stop if the angel can just keep jumping 100 squares up? One suggestion is maybe the devil can block her other routes like down, right, left. Yes, but the thing is, if we know that the angel's always moving up, like if like let's say like the angel, we're just programming the angel to always move up, just like again, like she doesn't think of anything but moving up. This strategy I claim does not work. Like if you replace the angel with just like a machine that always moves up, or like up and like left and right, just reasonably, you can still block it. So it's not like you can block off like, if you have the angel here, it's not like you need to block off like here, here, here. The angel's always going to keep moving this way, this way, this way. So if the angel keeps moving up, how do you think, what do you think is a good way to stop the angel? Thoughts? Block her up. Yes. If the angel is going to keep moving up, we should just stop her, right? Like just instead of investing all of your resources into like making all these like random little squares in her way, invest all your resources in building a huge wall in front of her, right? Which is not obvious, and it's not obvious that this works because the angel can move very fast, right? Like if if the angel, like if this is distance d, then you have to make this like like a pretty big distance, like distance, like I'd say like, let's say it's a power p and distance d, you have to make this like pd long or something. You have to make this like relatively long, but also like the devil, like the angel is coming really fast, so you have to find a way to build this wall efficiently. But it does work. The theorem is, of course, a fool of any power p loses to the devil. So even if the angel has power 1 billion, the devil can still win if the angel keeps moving up like a dumb person. And so here's the reason why. Okay, so the fool is limited to this cone of movement. What I mean by that is, well, it can't really go down, so it can only really go up or upright, or up left or upright, right? Specifically, like if you imagine, like for instance, the dude of power 2, right? Like they're over here. If you're only moving up and right, you're really limited to this cone of movement, right? That's the idea. And eventually you really can't leave this cone, right? So that's why I drew this cone here. So as long as we can block off, if we prescribe a distance d, and we can make this sufficiently long, like as long as we can cover all the possible spots in the cone, I think if you check it, something on the order of p times d, right? Yeah, so intuitively you should think it's like, okay, just build as far away as possible, right? But the thing is, you only have d over p time, but your length, the length of the wall is pd. Like this is always less than this. So the angel can if you try to like naively just build like block by block, like okay, like block and then block and then block, the angel's gonna run right past you. The angel's moving up Like the angel always
She can't
increases their
move
y
left.
coordinate. The angel can move left. It's just that the angel always strictly increases her y coordinate.
Wait, what if the angel just moves up 3 and then left 4? Wouldn't the angel like go outside the cone?
Yeah. Good. So basically what I'm saying is like for a specific p, you know, like if you have to move up like 3 up and 4 to the right, then p equals is like, you know, p is less than or equal to, sorry, greater than or equal to 7, right? You need at least power 7 to do that. And like, you know, if your suggestion is move like 3, 6, 1, 2, 3, 4, or power, I think power 4 actually. So it's like if you're up here and you move like, you know, like 3 up and like 4 to the right, something like this, you're still in the cone of movement. If the cone of movement depends on p, does that make sense?
Wait, wouldn't you be like a bit to the right of the cone?
3 up and 4 to the let me see, let me think about this. I think I see your point. So yes, I think I see your point. It's still a cone. Like of course the cone is like not actually a cone. Like it's not actually like lines. Like really what the cone looks like over here is like it's more squarish, right? I think that's what your point is. Like this is an approximation. Maybe I should have drawn it more like this. It's still a cone, like as you zoom out, right?
Oh yeah, okay.
That's the idea.
So yeah, it's more like I guess a little flat, I would think. Like this, okay.
Yeah. Okay, yeah. Also feel free to unmute. This is great. You guys should keep like engaging with this and whatnot. That really makes me happy. Okay. Does this make sense to everyone? Yeah.
Yep.
Okay. Oh, does someone have a question? No? Okay, great. So the idea is instead of like, you know, naively building the wall 1 block at a time, like, you know, you don't have enough time, right? Instead, what you should do, the idea is that as the angel moves up, the possible like spaces that she can go gets less and less. Like initially this is the cone, but then eventually it lowers to here, and then it lowers to here. And like right when the angel's right in front of the wall, like, you know, it's like a very small, like it's like almost like, I think it's like p, you know, it's like you only have to worry about p squares. So the idea is we build the wall recursively ahead in intervals. So we do it recursively in the following sense. So we do like, we pick a specific m, remove like in intervals, like pick an interval length m. And of course you have to make the wall thick enough, but you know, include this in m. So it's like, you know, if it's like power like 4, power 3, you need like a really thick wall, right? But in any case, the idea is that you build in intervals, right? So the first time, like in, you know, like when the fool gets half of the way there, you just made sure that you build every mth wall, right? So you like, there's a bunch of holes in the wall, but you're gonna fill them in later. But right now we've just like done every like, you know, 100th or something. Of course it's in terms of p, but every 100th block. Does that make sense? And now the reason that we did this is because once they're halfway there, they have half the space that they could possibly go to. So we don't need to worry about these guys anymore. We just need to worry about this guy. So we build every second square until, you know, and like we have less time to do it, but also we have half the amount of space we have to cover, so we can do it in time. And once you get a fourth of the way there, you know, now every second square has been filled, and now you can fill in every third square in this smaller interval, so on and so forth. Of course, D is going to be very big, very, very big in terms of P. I'm pretty sure it's like on the order of 2 to the 2 to the P. It's like very big. But you know, the devil can do it, and the fool is gonna run right into their wall. Does this make sense? Yeah. Okay. So that's what I mean by building the wall recursively. So we first build like block every pth square, and then, or sorry, every mth square, and then the second in every mth square, so on and so forth, until the wall is completely solid in front of the fool, and the fool can't go past. Okay. How much time do I have? Like 10 minutes? Oh, I'm kind of behind schedule. Whatever, it's fine. Alrighty. Does this make sense to everyone? Yes. Okay. Here's a part 2. You know, it's like feels like a very this strategy feels like a very specific strategy. You know, like if the angel just keeps moving up, like that's dumb, right? Like if the angel sees a wall right in front of her, why would she keep moving up, right? Like the angel at the very least can move like to the right, right? Like as in like just keep moving to the right, and and just like possibly dodge the wall. But here's a few results that you can get. So the first result that I actually want to talk about before I talk about the result in this slide, which is going to be later, I want to talk about a few results. One is that the same result holds with a lax fool. This is something I didn't include in my RAU lecture, but I would like to talk to you guys. A lax fool is a fool that doesn't always increase your y coordinate, sometimes move left or right, but doesn't ever go down. It just like moves left or right or up. So really it is like this, like, oh, I think, yes. So yeah, so it's like like when you're moving up, it's like kind of like a cone or something. But like when it's a lax fool, it's more like a little box, right? Like you could just keep moving to the right or something. Like it's no longer quite a cone. So you have to modify your arguments. But a lax fool, you can still win against the lax fool as follows. So if you imagine the angel right here, instead, we're going to split our attention in two parts. So first, we're going to devote half of our attention to building the wall. And we're going to devote half of our attention to closing in on the fool from the left and from the right. So, this is our first move. This is our second move. This is our third move. This is our fourth move. This is our fifth move, so on and so forth. You just keep closing in on the angel. So the angel just cannot keep moving to the left forever. And you just like slowly close in on the angel. So the angel just can't keep moving left and right forever. Eventually.
Wait, what does the lax fool do again?
Oh, sorry. Yes, the lax fool is a fool. So it always moves up, but also like the lax fool is a fool. So it never moves down. That's what I mean. It never moves down, but it can move left and right without going up. Does that make sense?
Oh.
And so, it's like if you just build the wall, the angel can just like keep moving like to the left or something, and it'll be fine for the angel. But the way you do it is like you assume the angel has a much higher power. By the way, I think it's like power like, I don't know. I'd expect it to be something like p squared. Just like assume the angel has much higher power because you're spending a lot of moves, wasting time. But it's okay. Just slowly box her in, so you know that eventually she'll have to leave the y coordinate, otherwise she'll be trapped. So she has to eventually go up here, and then the wall will be waiting for her. You donate half of your time to building this, like, again, this is not so mathematically rigorous, but you get the idea. You build this sort of blockade, I guess, if you imagine on the roads, like a blockade. You build a blockade on the left, you build a blockade on the right, and then up here, you slowly build this huge wall. So she can't go left, she can't go right, she has to keep going up. And a very similar argument, like, I think at some point they define like a real, like something like a relaxed fool of laxity 100. I'm not quite sure. I can show you guys the paper later. But like, there's certain variations of the fool that also don't work. But also, again, moving up is so restrictive. You could move to the right a little bit or even down. Like you can still, here's a possible strategy, for instance, maybe an angel who always goes away from the origin, and dodges all of the red squares can eventually win. False. An angel who always increases her distance from the origin loses to the devil. So for instance, like if there's an origin here, the angel keeps going this way, out, away from the center, right? The devils can catch her at some point. The angel will lose. This is so unintuitive, right? That means the angel has to go backwards at some point, which I mean, kind of makes sense, but also, so the angel just can't keep moving away, right? The angel eventually has to move back toward some red squares, right? So this is not so intuitive, but here's the proof. It's really easy. Imagine a kaleidoscope. I call it the kaleidoscope of doom. Imagine a kaleidoscope and the angel starts here. Every time the angel moves, 3 other copies of the angel move in their direction. So you should imagine really this as a kaleidoscope. So the angel moves this way, and that means all these angels move this way. So you're fighting against 4 angels effectively, right? So instead, you can imagine each of these, you can prescribe like mini devils here, right? Like you can imagine a bunch of mini devils here. Like the devil hires a bunch of mini devils and tells the mini devils, okay, every 4 turns, I'm going to give you a move and you could cross it off, right? So pretend, if you tilt your head, if the angel always moves away from the origin, this angel is basically a fool. All these guys are basically fools. So I can just hire all these devils and tell them, okay, you know how to drill for the fool. Imagine this guy has power 4p because you're giving them 4 moves in between because, I'm only giving you a move every 4 moves, but it's okay. Like you can win against any power p. So every 4 moves, I'm going to give you a block and then you can just execute the strategy of a fool on this sort of, wall. And of course, the details are not exactly right because this is a curved wall in the sense of, it's like a circle instead of like a line. But I think that, like the details are pretty clear. Like, it's like, I'm pretty sure you can turn into a square or something and still be fine. And then like quite literally apply the strategies just diagonally to these guys. So if you imagine this guy is 4p or I don't know, 10p, just to be really safe, just don't underestimate the angel, you can win. by just saying, okay, you go first, then you, then you, then you, then you. And eventually they'll fill up this entire circle as long as R is super duper big. Does this make sense? This is basically the strategy for the fool, except there are 4 angels. They're all fools, and you just deal with them one at a time. And you just assume they have 4 times the power because they can make 4 moves in between. Does that make sense? Yes? Cool? Wonderful. Cool. So, this is not so good. The angel, in some sense, has to keep zigzagging, right? Because the angel cannot always keep moving out. The angel sometimes has to move in. So you have to move out and in and out and in and out. You just have to zigzag your way through it. You can't just you can't keep going out. This does not work. You have to have a very complex strategy in some sense. And by the way, I think there's ignore the slide for a little bit. I want to write here. There's a quote from Conway that says something like, it seems really easy, but most strategies are too sensitive. Strategies are too sensitive. So for instance, if you guys want to suggest any strategies for the angel, feel free to, and I'll try to refute it on the spot. But the idea is that for most strategies of the angel is the angel's too sensitive to all the red squares. For instance, if your strategy for the angel is just get as far away from the nearest red squares. So for instance, every time you have a red square that's too close, you just go away from it, just directly away from it. If the angel's right here and the devil does something here, then the angel's and the angel moves this way. Can someone think of a very easy strategy to trap the angel here? Cheat, I guess. But you can only remove 1 square at a time. I don't know how you can destroy the entire infinite coordinate plane. You have to take things 1 step at a time. Just put the next double square in that direction so she bounces back and forth. That's a good point, but also, the angel can just move upwards, right? And you can only remove it 1 at a time, so you can't really surround her at any point. But this is a good idea. I think Isaac has the right idea. Sure, but it's an infinite coordinate plane. We have no big precedence here. Okay. So the idea, a very simple idea is, if the angel always jumps away from all these, squares, make a huge wall. I think Conway calls it make a huge wall 1 megaparsec away. Just make it super far away. Okay, just make a wall very far away, but make it very, very big. Okay, and then just coax the angel into this wall by just continually eating squares around the angel. So the angel's and just keeps running and running and running and running toward the wall. But it's not like she can do anything to stop it because all of these red squares are chasing her, right? So you can just chase her into this wall. Oh no, if the angel just adheres to the strategy like it's the Bible, the angel is going to run into this wall. Does that make sense? And if the angel is very sensitive to far away squares, if it can detect 1 megaparsec away walls, fine, just make a wall really close to her and make a lot of remove a lot of squares 1 megaparsec away, right? There's just a lot of really sensitivities in the strategies that the angel can abuse. When does the angel win again? We have not set a but we have not set a single power P for which the angel wins. I am trying to be the devil's advocate here. So far, we've just made an argument that the devil should, it seems like the devil has a really good chance. But before it seems so unintuitive, right? Because the angel has so much, it can move so far, right? But the devil, if the angel adheres to too strict of a strategy, then the devil has a plan. Oh, the definition of the angel winning is that the angel never gets trapped. So there's always a strategy for the angel not to get trapped. The devil can declare oh, you're gonna get trapped a billion seconds from now, and the angel's nope, and the angel just dodges it. That's when the angel wins. The angel never wins. The angel doesn't lose. If the angel doesn't lose, then the angel wins. That's the idea. Does that make sense? The game goes on till infinity. Or you can sort of think of it as no matter what game length they set, the angel always has a strategy. Does that make sense? Okay, so just in general, if your strategy is too sensitive, there are sensitivities that you can abuse, but that's not the worst part. Let me explain to you the worst part. And also, it's a really cool argument, by the way. But here's the worst part. Here's the reason why like the angel is like, it's like, it's like much worse than you thought. I call it the curse of efficiency. The idea is really simple, okay? Optimally, the angel should never visit a square she could have previously visited. This is not that hard to prove, right? Like for instance, imagine the angel's like chilling here. The angel's chilling right here, right? Let's say she jumps over here, then she jumps over here. That means the devil removed 2 squares. Let's say this square and then this square. And then now the angel's over here after 2 moves, right? What is a much more efficient way that the angel could have done this? Like, do you see how, like, why is this inefficient for the angel? What should the angel have done instead?
Just went to the just move to the right first.
Yeah, or not even move to the right first, just move directly there. You can move diagonally, right? So just move, do it in one move, as Alex said. Yes. Why is this strictly better for the angel? Well,
because the devil can place less squares.
Exactly right. The devil can place less squares, right? So the angel is strictly better. You're more efficient, so the devil has less squares cut out, and that's strictly better for the angel. So that's a very simple proof. That's the proof. We're done. Now, why is this bad? Here's a really interesting argument, okay? If the angel is never optimally visits squares she could have previously visited, so the angel should never revisit any of the squares she could have possibly gone to in less time, you can imagine all of those squares are blocked out by the devil himself, as follows. In efficient angel versus devil, the angel moves and then removes all of the possible squares because it makes no sense, right? If the angel's here, then the angel should never have to travel here. So we can just block it out. We can just pretend the devil removed it, right? Isn't that so cool? Isn't that such an interesting argument? Instead of the devil, like while the devil removes 1 square at a time, every time the angel moves, she's cutting off p squared of her own squares, right? Because you can assume without loss of generality that the angel is perfectly efficient. Does that make sense? Like the angel has no reason to ever go here, then here, right? Like if the angel did that, then the angel should have just gone here in the beginning. Does that make sense? So we can just assume that every time the angel could have visited a previous square, she just burns the square. Does that make sense? Does that make sense? I think it's a very intricate argument, but it's also really interesting, right? While the devil removes 1 square at a time, the angel removes p squared squares at a time. She's always tripping over herself. Like she has to go over here, and then she can't go over anywhere here, so she has to go up here. But then all these are, then all these guys are cut out. Doesn't it change based on the double strategy? No, and the reason is because, no matter what, the devil can just have less squares. The point is that the angel has to be perfectly efficient, because if it's not perfectly efficient, then the devil can have more squares, and that's strictly better for the devil, right? The devil never, if I gave the devil more squares, it doesn't hurt the devil. It strictly hurts the angel, right? So we can assume the angel is perfectly efficient. So the angel never visits any of those red squares. So the angel always burns everything in her path to make sure that she's efficient. You see? So it's like the angel's tripping over herself in some sense. Meanwhile, on the complete flip side, the devil can never make a mistake. What do I mean by this? Let's imagine you're the devil, okay? You're bored. You do not want to, you're bored. I don't know, you have homework or something. You don't really want to deal with the angel for the time being. So you go and play tic-tac-toe 1 megaparsec away over here. You go play tic-tac-toe with your friends. I don't know. You just play tic-tac-toe with them here. And the angel's jumping around, but she's jumping around aimlessly, right? She's kind of jumping there and then there and then there and then there. And then you just have to you just you just keep crossing out a bunch of random, you just keep playing tic-tac-toe with yourself, right? And then once you're bored of tic-tac-toe, you can just come back to the angel and okay, angel, we're going to play now. The devil that wasn't a mistake, This is strictly good for the devil. The devil didn't make a mistake because the devil never wastes time. The devil has an infinite amount of time. And in fact, this is strictly better for the devil than it was before, because not only is the angel basically has made no progress, the angel can't make progress, right? But also there are less squares on the plane. So it's strictly better for the devil. So even if the devil goes and plays tic-tac-toe in the corner 1 megaparsec away, it's strictly better for the devil. The angel has made no progress. In fact, it has made negative progress. The devil has made progress, even though he did nothing but play tic-tac-toe in the corner. Does that make sense? Again, really abstract argument. But the idea is that, the devil can do whatever he wants and he's still making progress. If he makes a mistake at any point, he could be like, crap, okay, fine. I'm going to pretend we reset the game because he's going to play tic-tac-toe, eons away, like a light year away. and just like plays tic-tac-toe for a little bit, and then afterwards like the angel like effectively like jumps away far enough from all the red squares, and then the devil's like, okay, let's restart, let's start again, and then the angel goes, and then the devil goes. But the devil's in a strictly better place than he was at the beginning. Does this make sense? Like the devil can do whatever he wants, right? Like, you know, and it's still removing squares and it's still making progress, while the angel is like tripping over herself. Does that make sense? Did someone want to say something? I heard someone muted.
Makes sense.
Yeah, makes sense. Okay, great. So it's so unfair, right? Is there any hope for the angel? Like, you know, the angel's tripping over herself, the poor angel. The angel can is removing like p squared squares every time, and the angel can't move up, has to keep zigzagging everywhere, while the devil can like play tic-tac-toe in the corner, right? Yeah, but the thing is, you know, like for, you know, like the time limit, you know, obviously the time limit, if the time limit's 1, the angel can win. But, you know, how do you know for the angel if the time limit isn't like 10 billion that the angel can't win? That's the question, obviously. And yeah, of course, the fact that there is no time limit is strictly hurting the angel. That's the point. That's why it's such an interesting problem, huh? So is there any hope for the angel? The angel is so maneuverable, but the thing is the angel has to be efficient and also can't move up and just has to have a very weird zigzag strategy. So is there any hope? This is a very hard problem. This problem was posed, as I said, in 1982. This was posed by Conway in 1982. And then he put out a, like, I think $100 prize if you can prove that the angel wins, and $1,000 prize if the devil can win. Because even though I spent a lot of time convincing you that the devil can win, he still believed that the angel probably wins. So he would be more surprised if the devil won. He put out this monetary prize, John Conway, and it took 20 years. It took until 2006 with 4 different people provided a proof simultaneously, which is really interesting, huh? But 4 different people provided a proof. One of them did it for p arbitrarily large. One of them did it for p equals 4, and 2 people did it for p equals 2. So like, you know, like imagine like being this guy. This guy must feel really bad. But, you know, in 2006, finally, after 24 years, Conway couldn't do it, but 4 different people eventually were able to show that p equals 2, the angel can win. I will provide a brief sketch for you today because the proof is really interesting and is also pretty understandable, but I do not want to go into the details because they're very technical. But I will give you an idea. The idea is that we turn the angel. This is the proof, by the way. This proof is by Mathey in 2006 for p equals 2. So you can imagine, you know, for p equals 2, you know, that's so small. And we just spent so much time arguing that, you know, the devil could possibly win. The angel's here. If the angel can go anywhere there, we show that for p equals 1, he loses. But for p equals 2, the angel can win. Huh. How do we show this? Like the angel has such a small sample space and has to zigzag everywhere. What's the proof? It's actually very conceptually simple. We turn the angel into a maze runner. Well, okay, here's the theorem, Mathey, 2006. The angel wins for p equals 2. So step 1 of the proof, before we turn the angel into a maze runner, is that we instead work with the nice devil. The idea is that, you know, if you have an efficient angel, the angel never revisits any of her past squares, then, you know, we can pit the efficient angel against a nice devil, right? A nice devil is a devil which doesn't remove any square that the angel could have previously visited, which makes sense, you know, because the angel, if the angel's already burning the square, then it makes no sense for the devil to actually remove those squares. You know, the devil's strictly better if he does not like waste his turns like that, right? Like as I said before, like the devil can't really waste turns, but like if you're skipping your turn, that's definitely wasting his turn, right? Like removing the square is strictly better than not removing a square. Anyway, it turns out that you don't even need efficient angel versus devil. You just need regular angel versus devil. As long as the angel agrees that to lose when she's trapped, you know, like the angel just can't keep going back and forth, because if the angel goes back and forth, then the nice devil's like, oh crap, I can't block these squares, right? But like, you know, the angel concedes if the nice devil makes this huge block. It turns out that this game is equivalent to this game. It's not obvious, obviously. Again, remember, this proof was in 2006, but I'm trying to give you the conceptual ideas here. The idea is that first we define the nice devil for the angel. Does this make sense? Yes. So basically, we create this new game between the angel and nice devil, where the nice devil doesn't remove any of the old squares and the angel concedes if they're trapped. So an efficient angel, correct. It's like nice devil. The reason it's a nice devil is like, you know, because the devil isn't removing any of the past squares that the angel could have previously visited or something. I don't know why he chose the word nice, but it is what it is. I think it's also a nice item. Okay. So without loss of generality, this is strictly better for we're going to show that the angel, like, oh, by the way, this is, the way that we show this is non-constructive. The way that we show this is like, if the devil can win here, then the nice devil can win here. So if we show that the nice devil cannot win here, then the devil cannot win here. Like a contradiction proof in a sense. In any case, we're going to show that the angel can win as follows. Without loss of generality, we just destroy the entire left plane. All of this is red. The angel starts here. The angel starts at 0, 0. All of this is going to be red. This strictly helps the devil, right? The devil is going to be okay with this. If these weren't here, then the angel can pretend that they're there. Like this is strictly, if we just make them all red, this is strictly benefiting the devil, right? We're not giving him one square, we're giving him like a lot of squares, like infinitely many squares, right? Okay. The idea is now as follows. We define the angel, we change the angel, okay? We're gonna blind her and we're gonna call her a runner. A runner is a blind angel. If you imagine closing your eyes, holding your hand out, like I'm holding your left hand out and running across your house by feeling the walls. Effectively, that's what the angel has to do. So the angel is blind, completely blind, but the angel every time runs as far as she can with her power. So in this case, if p equals 2, she can run over here, and afterwards she can run over here, and afterwards she can run over here, and afterwards she can run over here, so on and so forth, right? The idea is that the angel just blinds her, closes her eyes, sticks out her hand, and just runs, right? And just runs by holding her hand out. Angels can still be blind. I don't see that problem. Anyway, the angel just runs. Run, run, run. There are a few technical details to be ironed out, but that's the idea. The angel just sticks her hands out and keeps running. The question obviously is, okay, what? How the heck does this work? Here's a very simple strategy. If the angel just keeps running, what if we just make a mouse trap right up here? The angel's gonna run right into it and we can just close her in. Does someone see what's wrong with this? Here's a hint. We're playing against the nice devil. So why can't we just like make the angel like run up here and then like prescribe, there's going to be a mouse trap up here. And once you run into here, we're going to block you off. And now she's like trapped in here like a blind mouse. The issue is that, she ran through these squares. So the devil, being nice, can't block them off. But we know that this game is equivalent to this game. So if we can show that she can win here, then she has to be able to win here. Again, it's non-constructive, but we show that's the reason why we need the nice devil, okay? Because otherwise we could just make a very easy mouse trap. But because it's nice, you cannot block off any squares that are currently green, right? So the devil has to, the devil can't do that. And then the devil has to like just try to block her. Or eventually, like, just try to make something around her like this. But now you see, it's kind of hard for the devil to do that. And so this strategy works for p sufficiently large. I think p greater equal to 11. For p equals 2, you have to optimize it a little more. Instead of making these solid walls, you make them octagonal walls. Because the angel can move diagonally, right? So instead of assuming all these are solid, you assume all these are octagons. So you can like cut corners. You can cut this corner, 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 right? She's still sticking her hand out and running, but now since everything is an octagon, she just like snugly goes along here. Does this make sense? And it turns out that this is exactly good enough for p equals 2. This is just good enough for p equals 2. Again, I don't really want to go into the details because it is a very complex proof. And again, it was proven in 2006, right? It is very recent. But it turns out the angel can do it. For p equals 2, as long as the angel blinds herself, runs along with her left hand, she can do it. She can win. The angel can win, even though the devil does have a lot of tricks up his sleeve. Any questions? No? Okay. Well, I'll say a few words on this. A few more philosophical words, I guess. So this problem, believe it or not, I learned about this problem from a YouTube video. It's a very simple YouTube video. It's a very basic YouTube video. If you look up the angel problem on YouTube, you'll find a very layperson introduction to the angel problem. But of course, I know you guys are much better than that. You guys are math people, so that's why I give you guys this much more detailed introduction. But also like for the YouTube video, the funny thing is like if you go down to the comments, like no one understands it because they're like, oh, what the heck, like this doesn't make any sense. Like they don't understand anything about game theory. But it's a very good video. It's a very well made video. You guys should watch it. But I think it's such an interesting. I thought the reason that I wanted to tell you guys this today, I guess on a philosophical level, is that competition math, I think, is super fun. Of course, like I spent the past 4, 5, 6 years, 7 years, like doing competition math. Like competition math, like my life would not be the same without it. But I think on an objective level, even if like a lot of people tell you like, oh, learn higher math or learn different math, don't grind problems or whatever. Oh, you should enjoy math. I still think even on an objective level, you should learn higher math. And the reason is because higher math gives you a much broader view and a much more mature view of mathematics. And as a result, you can approach problems with a much broader mindset. It's not even a matter of just, oh, it's like you have to do higher math because it's not real math if you don't do competition math. I just think genuinely, like, of course, like you should do competition math. I think it's really important. However, I think if you want to get better at competition math, you should spend time thinking about recreational problems like this. Because it gives you a lot of intuition that you might not even know is even possible. And specifically for the angel problem, the funny thing is this problem I saw in 2020 and later at MOP 2020, I came across the following problem. 2019 ISL C7. This problem, I solved this problem because I looked at this problem. So if you guys want to look at this problem, by the way, it's a C7, which is really scary, really, really scary, especially if you're just starting math Olympiads. But it is a really simple and a really beautiful problem. And it borrows a lot of ideas from this angel problem. So if you guys want to take a look at this problem in your free time, feel free to. If you guys want to email me about it, feel free to. So I think it's just important for you to look at a lot of recreational problems and even just try out, like learning what a group is or something. I think Espen is teaching, like, I think basic complex analysis or something, which might be really complex for you guys. But in general, you should just try learning a lot of different kinds of math because it's a lot better to be varied than it is to be like to pigeonhole yourself. And also, if you guys want the references, this is the paper from Conway. Here it is. Lax fools. Here's the kaleidoscope. Here's the angel burning out their path. Can the angel really win? Cornering the devil. And here's the proof, the magnificent proof from Mathey. Here it is. You can see the maze runner here. I had to personally, I had to read these papers in order to give you guys a good, in order to understand this well enough to present it to you guys. So if you guys like reading papers, you guys can feel free to read this paper and talk about it. Feel free to email me about it. I'm really excited about this kind of stuff. Here's the proof. It's only 9 pages, which is surprising because it took 20 something years. But there it is. So that's the angel and double problem. And I hope you guys really enjoyed this lecture. I tried to make it not as technical, obviously, because you guys are doing a lot of math nowadays. And I wanted to give you guys a little fun break. And I hope I did that for you guys. Thank you guys so much for letting me speak. I think I'm speaking in a month. So if you guys are still around, I'll be happy to see you guys and say hi. But in any case, thank you guys so much.
Okay. So thank you, Sean. And the solution videos for level 1 through 4 will be uploaded to Google Classroom. And our next week's guest lectures are Vivian Han and Olivia Xu. And starting next week, Zachary Chung will be posting weekly physics challenge problems. And thank you for coming and have a good week.